Hello, this is Jeffrey Fox, the instructor of the Big Data Applications and Analytics course, School of Informatics and Computer Data Science curriculum, course motivation, which is Unit 2 of Section 1, which is the introductory section, and we're up to Lesson 11, Exploring Bags and Spaces. And this is a little abstruse, but sort of fun for me. Namely, we have lots of funny spaces in big data because we think of the space of all users, the space of everything sold by Amazon, the space of all movies in Netflix, the space of all words in a given language, and so on. And if we do what's called user-based collaborative filtering, we think of users in a space of dimension n, where every user is mapped into the items which they purchase, and we have it's a pretty large number of users, M users. Maybe M is many millions tens of millions for Netflix, and each of those has a vector associated running over the movies they've watched. So we have users represented as a vector in this item space, and maybe these users have a yes, no, but actually they could have three entries. Never seen the item, so that's sort of a neutral comment. Dislike this movie or like the movie. So they have a ranking or not ranked. It's important not to say not rank is 0 because there's a difference between not seeing a movie and not liking a movie. So an important issue if we compare users and vectors is unlike normal vector spaces. When you're living in Euclidean space X, Y, and Z, you never have no entry in Y. You have an entry in X, Y, and Z, because you may not know what it is, but you do have an entry in X, Y, and Z. You're at a particular place. But in the case of this space, it's different. You have this vector equal to the number of items in length, and you either have an entry in every component of that vector or a never seen flag. And so you use what's called the Pearson coefficient for discussing the relationship between vectors, and is effectively the distance which only sums over the items which are rated, and you have an entry for both of these users. And this is used by Amazon, Netflix, Last.fm, and so on. So this is not like your if you do a Euclidean distance, then you put 0 if the person didn't rank it, that would give you a very different answer from this one, which is the Pearson coefficient, and it doesn't have the usual properties of distances because it just excludes lots of components. So it violates all the conditions that give you the Euclidean spaces. Alternatively, if you do item-based collaborative filtering, you think of items as the points, and they're in a space of dimension m where there are m users. And now each item is represented as a vector in a user space, and the ratings of the users are the vector components. And we're looking for items that are near each other as measured between the distance between these vectors. And then, again, we use what is a so-called cosine measure, where we only sum over users, which is the components of the vector, which rate both the two things we're comparing. So again, these are an example of a funny distance. The third type of thing we have is content-based, and then items are represented by vectors in the property space. Maybe that has the color, the size, the things like that, and whether, like in books, the reading age, or whether it highlights Hercule Poirot or some other type of thing, or even the author of the books. And this type of content-based recommender engines, again, they again are dumb. Think of them as vectors, but they don't have quite the same features of having lots of non-valid entries. And this is used by Pandora, uses content-based recommenders, the so-called music genome. And again, content-based recommenders are also used by Amazon and Netflix. And so when you look at recommenders, they can be the three major classes, and you can mix them in complicated ways. They're user-based, item-based, content-based. They can be all thought about as points in a space, but the space had different sizes. The size equal to the number of items, the number of users, or the number of properties of items. So there's pretty interesting differences. And it's very useful to think about these points. You don't have to think about the points. And when you do large Hadron Collider analysis, quite what the points are, because each event is different. And so the vector size in the case of LHC is different for each event. So again, it has the same type of features. These are vectors in non-Euclidean spaces. And sometimes these things are called bags to emphasize they're not real spaces. That's particularly true in information retrieval, where you have bags of words. A given document is represented by the words in the document and the number of times each word appears. And you can usually always are looking at distances, because in almost all these problems, you're looking at nearness of items together. Is a given event or two events Higgs because they're near each other in some space? Is a movie likely to be one I watch because it's near another movie I watch, and so on. And we always choose distances which have some properties which are familiar, that distances are bigger than 0. And also the distance from A to B is equal to the distance from B to A. But they don't have some other important properties which are familiar from Euclidean spaces, like the so-called triangle inequality. Whether you need the triangle inequality for particular analysis is not so obvious, but there's certain clever methods which rely on the triangle inequality. Those will not work in these fancy spaces. And here we have the final comment on this field. So we're looking for nearest neighbors in this space in the various ways. For clustering, we're looking at dividing the space into subspaces. Each space has points that are near each other. In the case of k nearest neighbors, we're finding the k neighbors that are nearest to a particular point. And say this is the two things. This is the k nearest neighbor described here. You find a fixed number like 3 or 10 or something items near what you're looking at another item, or users that are near another user. And the other one is to divide the space into regions. That's called latent factors or topics in the case of information retrieval. And that's clustering. And those consist of points that are near each other. And there are other related algorithms, Gaussian mixture models, latent semantic analysis, latent deletion allocation, which use very sophisticated models, more sophisticated than clustering, to determine topics or latent factors, which are effectively ways of representing spaces and dividing them into regions where the points in the regions are near each other. So in the case of Google News, you want to have all the items that are relevant for the current news item, I know, about Ebola, or about the president, or about the election. It's not just a simple mapping to words. It's a complicated set of criteria, which is gotten by training by a relatively pretty sophisticated analyses, which are represented by these models here. And we will not go into these models in this class, but the more sophisticated machine learning course would do that. So thank you very much. This is just telling you, look at distances and look at funny spaces. That's what you'll need in the big data world. And then, of course, you have to visualize these spaces. That's what we do when we map these spaces into 3 dimensions, so we can visualize them. Thank you very much.